I'm Raiaan from Roots of Unity, and today we're going to cover the basics of trigonometry. In this video, I'll be covering fundamental graphs, inverse functions and reciprocals, exact values, and so on. We'll also learn how to find the roots, solve equations, and how to prove identities. Now, the basics of this chapter are things you know already. Let's refresh our memories. There are three fundamental functions to consider: sine, cosine, and tangent. Using this triangle as a reference, let's recall SOHCAHTOA. Sine is defined as oppo by hypo with reference to theta, cos is adjacent by hypo, and tan is oppo by adjacent. There are some exact values to remember when solving related equations. There will be no need for a calculator. Using these triangles as references, we can calculate the individual values for 30 degrees, 45 degrees, and 60 degrees very easily. Pause the screen to take a look at the table. Moving on, we'll examine the graphs of the functions in question. Both the sine and cos curves are wave functions for all values of x. The period is 360 degrees and the range lies from -1 to +1. You'll notice the only difference here is a phase shift of 90 degrees horizontally. If we draw a circle with radius 1, these graphs will make more sense to you. Since sine equals to y by r, you'll see how the value of y goes from 0 to 1 and so on. The same approach works with x for the cos function. On the other hand, the curve for tan theta is a bit more different. The curve exists for all values of x except say 90, 270 degrees, etc., where you can notice the vertical asymptote. So basically, x does not equal to pi by 2 plus kpi. The period of tan curves is 180 degrees, while the range extends from -infinity to +infinity. The curve approaches infinity when it reaches the asymptotes. Now that we remember what the curves look like, let's look at some key concepts. Do not confuse inverse trig functions with the reciprocals. When a sine function is inverse, you're shifting it to the right with a power of -1. You'll see the function on your calculator. This occurs similarly with cos inverse and tan inverse. This will help you later on to find the roots of the equations. However, the reciprocals involve you shifting the function to the denominator. These reciprocals have their own names, which is secant or sec, cosecant or cosec, or cotangent or cot accordingly. Pretty fancy, right? Moving on, the relation between sine, cos, and tan is pretty obvious. Tan equals to sine by cos, just like that. You should also recall the Pythagoras theorem. In this equation, if we substitute x and y with the trig counterparts, we can cancel out r square on both sides. This leaves us with sine squared theta plus cos squared theta, which equals to 1. It's a very fundamental identity. You will need this in the future. Time to look at symmetric properties. Firstly, we can recall that the period of a cos curve is 360 degrees. Hence, if we keep adding or subtracting 360 from theta, you'll get the same result. Also, if you haven't noticed yet, the curve for cos theta reflects on the y-axis. This is the even property of the curve, which means cos minus theta equals to cos plus theta. In the translation property, we can see that if we shift the value of theta by 180 degrees to the left, we get negative cos theta. It is easier to understand if we can visualize the relation. If we merge our two findings, we'll see that cos 180 minus theta also equals negative cos theta. By the way, do not mix up minus cos theta, a flip on the x-axis, with cos minus theta, a flip on the y-axis. Also, a simpler way for you to visualize what's going on would be with the help of a circle. We know that cos theta equals to x by r, and hence has no relation with the value of y. So, the negative region of cos theta would be when x is also negative. R is always positive because of the modulus. By now, you should have a clear idea of how these properties work. Pause the video and take a look at the properties for the sine function. The main difference here is how sine is an odd function, which means the graph is symmetric about the origin, instead of being mirrored like cos theta. Since sine equals to y by r, The negative region in this scenario coincides with when the value of y is negative. A similar case happens with the tan function. Note that tan theta has a period of 180 degrees. It follows the odd property similar to the sine graph. Since it involves both x and y, the positive regions lie in the first and also the third quadrant, where the negative signs cross each other out. Well, that was quite the review. Now, let's move on to problem solving, which should help you get right back on track. Here, I made use of the symmetry properties from earlier to find these answers without using a calculator. As I said, these exact values are very helpful to keep in mind. Take note of the general method used as we progress. Now, we'll take a look at how you can use triangles to solve these questions. Here, we have tan x equals to k, where k is a positive constant. How would we find the following in terms of k? In the first question, we can simply make use of the symmetry properties to state that tan pi minus x is the same as minus tan x. Leading to minus k. In the second part, we can illustrate the triangle. We assume the adjacent of x to be 1. When you subtract x from pi by 2 in this right-angled triangle, you are left with the third angle, which is the theta. So, from theta's perspective, oppo by adjacent would result in 1 by k. Now, in the last instance, they're asking for sine x. We make use of the Pythagoras theorem to find the expression for the hypotenuse. Plugging that into the function, we end with k by root over 1 plus k squared. Next up, we're going to try and find the roots of these equations. Pause again if you'd like to try. Now, don't be scared by how much writing you see on the screen. The general process behind each question is pretty much the same. Number 1 portrays it pretty well. You take sine inverse and find the basic acute angle, which is 30 in this case. Then you find the remaining angles within the specified interval, making sure they're in the proper regions. For number 2, the values of theta fall in the negative regions, namely the second and the third quadrant. Make sure to change the interval in accordance to the question. For making the calculation easier, I assume 2 theta minus 50 to be alpha. Do not forget to rearrange and make theta the subject at the end. Always check whether you've covered every value within the range. Drawing a little diagram helps you keep track more easily. For example, you can see that all of these expressions fall in the same 2 quadrants, while being inside the interval. In question 3, we got rid of minus 45 here, since it fell out of the interval we were working with. There's 2 more problems for you to contemplate for finding the roots. In number 5, when you inverse tan and bring it to the other side, the inverse and the tan bits cut each other off, leaving you with just 60. A quick note is to keep track of how many cycles you have to keep adding 362 is by noting the coefficient of the theta. It was a lot of words, but basically here in this case it's 3, meaning the value of theta has been cycled through thrice. And lastly, in number 6, we have theta being negative, which means the range gets flipped while working with alpha. For our last 2 problems, we'll take a look at identities. Here, you should recall how sine by cos equals to tan and sine square x plus cos square x equals to 1. In the first example, we add the 2 fractions together and expand. We see that we end up with sine square x plus cos square x, which we will substitute with 1. This will allow us to add 1 plus 1 and take 2 as common, and lastly cut off 1 plus sine x, leaving us with the RHS proven. In this particular case, we dealt with the numerator and denominator separately to make the process simpler. Substituting tan square x with sine square x by cos square x, we obtain the following expressions. In the second part, we replace cos square x plus sine square x with 1. Plugging this into the equation, we get cos square x minus sine square x, and our aim is to make the entire expression expressed with sine x. So we substitute once again, this time removing cos square x, and hence end up with the right hand side proven. So now you might have the question, why is trigonometry so important? Its uses range all over the field of science and engineering, from alternating currents in appliances to radio waves, sound waves, and even simple harmonic motion and projectile motion. You'll notice day by just how much of an impact trigonometry has in our lives. The shape of the curves provides a very handy platform to implement various concepts even beyond reality. The first video ends here. If you've reached this far, thank you for watching. While this video is more of a summary of what we already know, we'll start to expand on the more complex scenarios in the upcoming videos. Until next time.